All right, so what you've seen is that, in fact, the deep linear networks do usually end up at the linear regression solution, or at least close to it. But the key thing is that they take very different trajectories to get there. So this is really just saying that there's a separation between the dynamics of learning and the asymptotic solution that you find once you run to convergence. And a lot of the interesting features of deep learning dynamics, at least in this deep linear network setting, they're really about the dynamics, not the end solution you arrive at. And one lesson that this shows you is that gradient descent is not invariant to the parameterization you choose. So we are solving a very similar problem, right? We're just taking this linear map and factorizing it into the product of matrices, but doing that, sort of adding this depth, massively changes the learning dynamics for these networks. And to better understand where this is coming from, let's just dig into this for a bit more time. So when we say that we have a deep linear network, what we mean is that the mapping from the input to the output is linear. And we can always rewrite that as just a linear map. But remember that we're going to plug that into our objective function, or loss function, or error function, which here I've been using the squared error. So this is where nonlinearity has re-entered the picture. Right? We're going to compare the target values to what the network is producing at the current point. And then it turns out that when we start solving our minimization problem to do learning, if you look at this minimization problem, even for this deep linear network case, it's non-convex once you have one or more hidden layers. And that's why this is an interesting toy model if what you're interested in is some of the basic features of learning dynamics and non-convexity. And the picture that's sort of emerged from this tutorial so far is that in a shallow network, you've seen that training is very rapid and just follows a simple exponential approach to low error. Whereas in the deep network, you see many sigmoidal stage-like transitions where the error drops a little bit. Training is generally slower. And those are some of the key differences between shallow and deep networks when it comes to dynamics. Now, the other difference between a shallow and a deep network is that the structure of the hidden layer, the similarity structure that we explored using representational similarity analysis, can change how deep networks are going to generalize. And essentially, if you get a new item, what they're going to do is generalize their decisions to items that are deemed similar according to the hidden representations in the network. So similarity-based generalization, it can work extremely well, but it's also a risk because similarity is definitely not causality. You're not really understanding something fundamental necessarily about the hierarchy of items. You're just finding a way of organizing the hidden representations so that items in this hierarchy that are nearby are a little more similar to each other. One example of this, which is prominent in psychology, is the phenomenon of illusory correlations. So if you go to a young child of the right age and you ask them, does a shark have bones? They might say yes. This is famously shown by Susan Carey at Harvard. Now, they never could have actually seen this in practice because sharks don't, in fact, have bones. They have cartilage skeletons, I'm told. So where did they get this idea that sharks have bones? Well, we can sort of work out a toy model of this using our little hierarchical example and just adding in one new feature to play with. So we have our hierarchy, the shark is sitting over here, and we're going to have a feature that you're supposed to predict, which all of the animals have, none of the plants have, and the shark is the one exception animal that it doesn't have. And your job is to test deep and shallow networks predictions for whether they think a shark has bones when you train them on this data set and this feature.